Hey guys, welcome to day 12. It's kind of hard to believe, but it has been, I believe, a month since I've seen you guys. I think Friday the 13th was our last normal day of school, and now it is Monday the 13th. 1 month later, hopefully, 1 month from now, I'll be seeing you guys face to face. All right, so chapter 8, bonding concepts, Lewis structures, a little bit more detail. Hopefully, at this point in the game, you are comfortable drawing Lewis structures for just single atoms. You know, group 1 elements get 1 dot, group 13 elements get 3 dots. Remember that we've skipped the transition metals because, well, they don't always abide by the same rules that the representatives do. So, a couple things real quick. One thing that I want you to remember is a little saying that says, have no fear of ice cold root beer. Okay, have no fear of ice cold beer. And remember, those are the elements that like to form in pairs. So there are 7 diatomic elements, and that's just an easy way to remember them. A couple of things, most of them are joined by single bonds. Oxygen is joined by a double bond, and nitrogen is joined by a triple bond, okay? And Br is bromine, okay? All right, so got that out of the way. So you guys know which elements exist in pairs. That is kind of important. So hydrogen, the halogens are all connected by single covalent bonds, okay? Another thing I want you to consider is when you are doing dot structures, the number of singles represents the number of bonds that an element can form. So hydrogen has 1 single. Hydrogen can form 1 bond. Now we're really dealing mainly with the nonmetals. So if we skip over to the carbon group and we look at carbon, carbon has 4 singles. Carbon can form 4 bonds. Okay, by the time you get to nitrogen, nitrogen has 3 singles. Nitrogen can form 3 bonds, and that goes for sulfur as well. And really, you can pick any of the halogens. They're all going to have the same dot structure. When you get to the halogens, they have 1 single, and therefore they can form 1 bond. So remember, singles like to mingle. The number of singles represents the number of covalent bonds that can form. All right, moving on out. Okay, let's talk a little bit about when doing molecules. Okay, when doing molecules, I think your best strategy is to count electrons. Now, when I say count, we're really only talking about valence electrons. So let's take water, for example. Hydrogen gets 1 dot. But if you look at the formula, there are 2 hydrogens. So we get 1 plus 1, and I'll go ahead and change color for you. Oxygen has 6 valence electrons, so we know that if we're going to draw a Lewis structure for water, we should have 1 plus 6 plus 1 dots, and that would get us up to 8 dots in total. Now, one thing to note, hydrogen will never be in the middle of a molecule. It can only form 1 bond. Halogens will never be in the middle of a molecule. They can only form 1 bond. So really, it's primarily carbon and nitrogen, oxygen, and sulfur that you're going to find in the middle of molecules. So we know that oxygen is going to be in the middle of the molecule, and I like to start with the dot structure for oxygen. We know that it gets 6 dots. It has 2 lone pairs, and it has 2 singles. And then what I'm going to do is I'm just going to kind of go in and I'm going to fill in hydrogens where I know that they belong. And if you look at the Lewis structure for water, you guys should notice that there are in total 8 valence electrons, and or 8 total electrons. So if you look at my structure, it certainly does. All right, so let's move on to carbon dioxide. Okay, if you look at the structure, it has 1 carbon. So 1 carbon gets 4 dots. Now, if you look at the structure, it actually has 2 oxygens. Oxygen getting 6 dots, so we get 2 dots for each oxygen. So when we go to do the structure for carbon dioxide, we should have 16 total dots. Now, this can get a little tricky. Carbon dioxide is kind of a complicated molecule. You could try to do this with single bonds, and you got to start someplace. But remember, oxygen likes to form 2 bonds, carbon likes to form 6 bonds. I know my structures don't look very good over here, and that's because the formatting was kind of messed up. But I know for this particular molecule that carbon is going to be in the middle. And I know for this molecule, the oxygens are going to kind of flank it on either side. And what I'm going to kind of start to do here is just show my lone pairs. I know that oxygen has two lone pairs. So here's a single, and there's a single. Here's another single and a single for oxygen. And then I'm going to switch back to pink for carbon. There's a single, a single, a single, and a single. So what I could do to clean things up for you guys a little bit is draw it like this. I do like you guys to show unshared pairs, especially the beginning stages of drawing Lewis structures. And remember, a line represents two electrons. So that would be the structure for carbon dioxide. And if you're to count the dots, you should get up to 16. Remember, one dash represents two dots. So regardless of what structure you're looking at, you should get up to 16 dots, okay? Let's see, move on to the next one. Let's do an ion. So cyanide. Cyanide is your Cn-1 ion. I'm going to change over here. So carbon is going to get 4 dots. And we know that nitrogen gets 5 dots. So we also have a negative symbol, and that negative symbol tells us that there is one more electron. So all said and done, when we draw our Lewis structure for cyanide, we get 4 dots for carbon, 5 dots for nitrogen, but the negative symbol indicates that there is one more electron going on. And if I were to do this, carbon typically likes to form 4 bonds, and what's going to happen is you're going to end up with a number of electrons that doesn't necessarily kind of fit our standard model. So carbon, those are 3 singles, and then I'm going to draw that adjacent to nitrogen. I think I did nitrogen in pink. So that accounts for 6 of our electrons, but you realize very quickly that neither one of these elements has an octet. So what you kind of got to do is you got to figure out how those electrons are arranged. And if you look at the structure, I have 4 plus 5 plus 1. So I get 10 dots, and maybe I should change one of those dots on carbon to a different color. So there's the 4 dots that belong to carbon, and maybe I can add in that extra electron, that -1 electron that it picked up someplace to show as that additional electron. So nitrogen's got its 5 electrons, 8 when it starts to share. Carbon's got its 4 electrons, but it shares a couple with nitrogen and it picks up 1 more. So this would probably be the best Lewis structure for cyanide. If you wanted to clean it up a little bit, you could just say triple bond between nitrogen, and each element has an unshared pairs. We should also probably show that negative symbol someplace in there as well. So guys, we can do these for molecules. We can also do them for many polyatomic ions. Here's some Lewis structures that I want you to be able to do. I'm just going to kind of do them with you. So when you look at hydrogen fluoride, hydrogen gets 1, fluorine gets 7. So all in all, our final structure should have 8 electrons. When you look at, I'm going to zoom in a little bit. When you look at nitrogen, nitrogen should have 5 plus 5 more. So all said and done, I should have 10 dots. And if I were to do nitrogen, triple dots, or triple bonds, and then 2 singles. All right, let's do ammonia. So ammonia, we've got nitrogen. I'm going to change colors. Nitrogen gets 5, but we've also got 3 hydrogens. So I'm going to say 5 plus 1 plus 1 plus 1, which would give us a grand total of 8. And if I were to do the structure for ammonia, there's nitrogen's 5 dots, and I could even kind of go back and fill in these hydrogens in a different color. So we've got, looks like 8 total dots. All right, so what about methane? Okay, methane should have 4 for carbon, plus we're going to get 4 more electrons because we have 4 hydrogens. If we put carbon in the middle, then we can surround it by 4 hydrogens, each bringing 1 more dot. Hydrogen ends up with this duplet. Carbon ends up with this octet. Moving on, carbon tetrafluoride. So carbon is going to get 4 dots. And for fluorine, I'm just going to show multiplication. Each fluorine has 7 dots, so 4 fluorines are going to bring 28 dots to the party. So all in all, we should have 32 dots. I think I can do this pretty quickly. Just remember that 1 dash represents 2 dots. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. Now, nitrogen oxide with a +1 charge, a +1 means that it's lost an electron. So nitrogen gets 5, oxygen gets 6, but then we're going to subtract out 1 electron. So all in all, nitrogen monoxide should have 10 electrons. I don't remember doing this one off the top of my head, but if I had to guess, it's probably going to be a triple bond between oxygen and nitrogen. So 10 total dots. Each element has its octet. So I think I'm pretty confident that that's going to be right for nitrogen oxide. Guys, let's look at some of the exceptions to the octet rule. Let's see, boron. And actually, I don't know if I really want to do these right now. I guess I can show you the diagrams real quick. Just realize that there are exceptions. And what's going on here is that sometimes D sublevels get involved. So when you look at boron trifluoride, you should end up with, it looks like 21 plus 3 should be 24 dots. And I've got a couple of different situations that represent that. Sulfur hexafluoride does exist. Sometimes sulfur lets its D sublevels get involved in bonding. So sulfur, if you want to do the math with me, sulfur gets 6 dots and fluorine gets 7. So 42 plus 6, all in all, we should have 48 electrons for sulfur hexafluoride. Phosphorus pentachloride should have, let's see, phosphorus is, I believe phosphorus is in the same group as nitrogen, so 5. Plus we have 5 chlorines, bringing 7 electrons each. So I think phosphorus pentachloride should have 40 total electrons, okay? Sometimes elements in the third row can exceed the octet rule. It can get a little bit complicated. Sometimes these d orbitals can get involved in bonding, but just realize, you know, simple Chem 1, we always kind of stuck to the octet rule. Just realize in the real world, sometimes elements don't always follow the octet rule, and structures can get a little bit complicated. All right, so guys, I've given you some structures to do in your homework. Some of them are for elements, some of them are for molecules. And my strategy is going to be, you know, think about how many singles like to mingle. So think about how many elements or how many bonds each element will want to form, but also do yourself a favor and count electrons. So if you're doing a molecule, you know, realize that each element gets a unique number of valence electrons, you know, assuming that they're neutral. And if you can kind of tally those up, it might help you a little bit with your homework. So don't forget, if you guys have questions, you can leave a comment in Google Classroom, or feel free to leave me a private email. All right, guys, it's been a month. Hopefully next month I'll get to see you. I miss you guys. I love you guys.